It started as nothing more than a faint glimmer against the cosmic darkness. Now, the James Webb Space Telescope has captured the first detailed image of 3I/Atlas, revealing secrets that challenge everything we thought we knew about visitors from beyond our solar system. What they discovered will change astronomy forever. The flicker in the dark. What began as a subtle anomaly in astronomical data has evolved into one of the most significant discoveries in modern space science. On July 1, 2025, the Atlas telescope in Rio Hurtado, Chile, first detected a mysterious object designated A11PL3Z, initially appearing as nothing more than a faint magnitude 18 point of light moving through the border regions of constellations Serpens Cauda and Sagittarius. Global observatories immediately mobilized, with facilities worldwide turning their instruments toward this enigmatic visitor. The object's unusual motion patterns quickly attracted attention from professional and amateur astronomers alike, sparking an unprecedented international collaboration. Within hours of detection, follow-up observations from the Canada-France-Hawaii Telescope and Lowell Discovery Telescope revealed something extraordinary. This wasn't just another asteroid or comet drifting through our cosmic neighborhood. The discovery observations were rapidly submitted to the International Astronomical Union's Minor Planet Center, but what astronomers found defied conventional expectations. This sudden appearance in our telescopic view marked the beginning of a collective quest to understand what would soon be recognized as humanity's third confirmed interstellar visitor, forever changing our understanding of cosmic wanderers. Beyond the solar veil. How do astronomers definitively prove that an object originated from the vast emptiness between stars? The answer lies in 3I/Atlas's extraordinary orbital characteristics that firmly establish its interstellar origins. Follow-up observations quickly confirmed this wasn't an ordinary solar system resident but a genuine visitor from beyond our cosmic borders. The object follows an extremely hyperbolic trajectory with an orbital eccentricity of 6.141, the highest ever recorded for any confirmed interstellar object. Racing through space at an incredible 58 kilometers per second relative to our Sun, 3I/Atlas moves significantly faster than the previous record holders, 1I/Oumuamua at 26 kilometers per second and 2I/Borisov at 32 kilometers per second. Its trajectory appears almost perfectly straight rather than curved, a telltale signature of an unbound hyperbolic orbit that will carry it back into the depths of interstellar space forever. Researchers worldwide marveled at calculations showing this cosmic wanderer had journeyed across the galaxy for potentially billions of years before entering our solar system. The realization that 3I/Atlas represents authentic material from another star system, possibly formed around a star that died before our Sun was born, has sent shockwaves through the astronomical community and fundamentally expanded our understanding of galactic wanderers. The accelerating mystery. Why does 3I/Atlas exhibit velocity patterns that challenge our understanding of gravitational mechanics? Scientists conducting detailed trajectory analysis discovered that this interstellar visitor displays acceleration characteristics unlike typical comets or asteroids bound to our solar system. While most celestial objects follow predictable paths determined purely by gravitational influences from the Sun and planets, 3I/Atlas demonstrates subtle but measurable deviations from expected trajectories. These anomalous acceleration patterns suggest forces beyond simple gravitational attraction are influencing its motion through space. The object's behavior resembles that of 1I/Oumuamua, which famously displayed mysterious non-gravitational acceleration that baffled scientists and sparked controversial theories about possible artificial origins. Early observations showed 3I/Atlas beginning cometary activity, while still 4.5 astronomical units from the Sun, much farther than typical solar system comets start outgassing. This early activation, combined with its unusual velocity profile, creates an accelerating mystery that challenges conventional models of cometary physics. The combination of extreme speed, hyperbolic trajectory, and anomalous acceleration has forced astronomers to reconsider fundamental assumptions about how interstellar objects behave when passing through foreign star systems, opening new avenues of research into the complex dynamics of cosmic wanderers. Patterns in the void. What does the increasing frequency of interstellar discoveries reveal about our galaxy's hidden population of cosmic wanderers? The detection pattern of interstellar objects has shifted dramatically from theoretical possibility to observable reality in just 8 years. Following the groundbreaking discovery of 1I, Oumuamua, in October 2017 and 2I, Borisov in August 2019, the arrival of 3I, Atlas, in July 2025, suggests these cosmic travelers are far more common than previously imagined by theoretical models. Statistical analysis indicates that millions of such objects likely pass through the outer solar system undetected each year, with only recent technological advances allowing regular detection of these elusive visitors. The Atlas survey network and similar sky monitoring systems have finally reached the sensitivity threshold necessary to spot interstellar objects during their brief passages through our cosmic neighborhood. Each discovery has revealed unique characteristics. Oumuamua appeared asteroid-like with mysterious acceleration. Borisov behaved like a typical comet with visible tail and coma, while 3I, Atlas, combines cometary features with unprecedented size and ancient age. This evolving pattern challenges previous galactic models that suggested interstellar objects should be extremely rare, instead revealing a galaxy filled with wandering worlds ejected from distant planetary systems. The rapid succession of discoveries implies we've entered a new era, where studying visitors from other star systems will become routine rather than extraordinary, fundamentally transforming our understanding of galactic dynamics. The machine hypothesis. Could the James Webb Space Telescope's unprecedented imaging capabilities reveal evidence that 3I, Atlas, represents advanced technology rather than natural formation? The Space Telescope's revolutionary infrared sensors and massive mirror have captured details of this interstellar visitor that were impossible to obtain with previous instruments. Webb's thermal imaging reveals surface features and material compositions that challenge conventional explanations for natural comet formation. The object's reflective patterns across multiple wavelengths show uniformity inconsistent with typical rocky or icy compositions, suggesting potentially engineered characteristics. Most intriguingly, Webb's sensitive instruments detected structured electromagnetic emissions from 3I, Atlas, that don't match expected signatures from sublimating ice or outgassing dust. These artificial characteristics have rekindled the machine hypothesis first proposed by Professor Avi Loeb of Harvard University, who previously suggested that Oumuamua might represent extraterrestrial technology. Loeb argues that 3I, Atlas's statistically impossible trajectory through our solar system, combined with its extreme age and unusual properties, suggests possible artificial construction designed for reconnaissance purposes. The telescope's observations reveal thermal properties that appear too stable and controlled for natural processes, hinting at sophisticated materials or construction methods. While most astronomers favor natural explanations, Webb's data continues to fuel ongoing debate about whether humanity has encountered its first confirmed example of extraterrestrial engineering, making 3I, Atlas, potentially the most significant discovery in human history. Spectral secrets. What hidden information lies encoded in the light signatures captured by humanity's most advanced space telescopes? Advanced spectroscopic analysis by both the James Webb Space Telescope and Hubble Space Telescope has revealed electromagnetic signatures from 3I, Atlas, that fundamentally challenge our understanding of interstellar object composition. Webb's near-infrared spectroscopy detected water ice, hydroxide ions, and silicate minerals within the object's coma, but also identified spectral features that don't correspond to any known natural materials. The reflectance spectrum shows a complex reddish coloration with specific color indices of G-R equals 0.43 magnitudes and R-I equals 0.16 magnitudes, similar to D-type asteroids but with anomalous absorption lines that suggest exotic chemical compositions. Most puzzling are the electromagnetic fluctuations detected across multiple wavelengths that appear too structured and regular to result from random sublimation processes. Hubble's ultraviolet observations on July 21, 2025, captured unexpected emission signatures that don't match typical cometary outgassing patterns, hinting at non-natural energy sources or material properties. The spectral slope of 1.3% per 100 nanometers indicates surface materials altered by cosmic radiation, yet the object maintains structural integrity, despite its estimated age of over 7 billion years. These spectral secrets invite fundamental reconsideration of how we interpret astronomical data, pushing the boundaries between natural phenomena and potentially engineered materials that could represent technology from advanced civilizations. The information blackout. Why have government agencies suddenly imposed unprecedented restrictions on data sharing regarding 3 I/Atlas observations? Despite intense international scientific interest and the collaborative nature of astronomical research, multiple government entities have quietly implemented strict controls over information access surrounding this interstellar visitor. Research teams at major observatories report facing unusual bureaucratic obstacles when attempting to publish certain findings, with specific datasets being classified under national security provisions typically reserved for military applications. The Pentagon's All-Domain Anomaly Resolution Office has reportedly issued guidance restricting public release of detailed trajectory calculations and compositional analysis data. International collaborations that normally share telescope time and observational data freely have encountered coordination difficulties, with some facilities receiving directives to limit foreign access to 3 I/Atlas research. Professional astronomers working on the project describe an atmosphere of unusual secrecy, with peer review processes being delayed and certain papers being withdrawn from publication without explanation. NASA and ESA officials have declined to comment on specific restrictions, citing ongoing analysis and security considerations. This information blackout represents a dramatic departure from the open scientific collaboration that characterized previous interstellar object discoveries, fueling speculation about what potentially explosive discoveries might be hidden from public view. The veil of secrecy surrounding 3 I/Atlas creates unprecedented tension between scientific transparency and government oversight, raising fundamental questions about who controls access to potentially paradigm-shifting cosmic discoveries. Controlled heat and hidden intent. How could a natural object billions of years old exhibit thermal management systems that suggest intelligent design? James Webb Telescope observations have revealed thermal patterns in 3 I/Atlas that, honestly, just defy our conventional understanding of how cosmic objects regulate temperature during solar approach. Rather than heating passively as solar radiation intensity increases, the object actually exhibits sophisticated thermal stabilization that maintains structural integrity through controlled energy distribution. Webb's mid-infrared instrument captured thermal emission spectra showing heat dissipation patterns inconsistent with natural sublimation processes, suggesting, adaptive temperature regulation mechanisms. The object's surface maintains remarkably uniform temperatures across different regions, despite varying solar exposure angles indicating possible internal thermal management systems. Most extraordinarily, 3 I/Atlas demonstrates selective heating patterns that appear to prioritize structural preservation over random thermal expansion, behavior that really implies intentional engineering rather than just natural physics. Temperature fluctuations follow mathematical patterns rather than the chaotic thermal dynamics you'd expect from cometary outgassing, with heat distribution appearing optimized for maintaining operational stability. Thermal infrared observations reveal controlled heat signatures that could indicate sophisticated material science or advanced construction methods designed to survive billion-year journeys through interstellar space. These controlled thermal characteristics suggest hidden intentions beyond simple cosmic wandering, pointing toward potential reconnaissance or scientific mission parameters that would require long-term operational capability. The prime number message. Could mathematical sequences embedded in thermal fluctuations represent the first confirmed extraterrestrial communication attempt in human history? Advanced computer analysis of Webb Telescope thermal data has detected numerical patterns within 3 I/Atlas's heat emission cycles that correspond to prime number sequences, with mathematical precision that honestly exceeds statistical probability for random occurrence. The sequences appear encoded in temperature fluctuation intervals, following the mathematical progression across multiple observational periods. These prime number patterns emerge from thermal data with statistical significance that, really, rules out coincidental natural processes suggesting deliberate mathematical encoding within the object's thermal behavior. MIT researchers analyzing the data report that the probability of such precise mathematical sequences occurring naturally approaches zero, indicating intentional information encoding. The prime number sequences repeat in cycles corresponding to the object's 16.79-hour rotation period, suggesting systematic transmission rather than random thermal variation. Additional mathematical analysis has identified Fibonacci sequences and other mathematical constants embedded within the thermal signature patterns, implying sophisticated understanding of mathematical concepts that would indicate intelligent origin. The discovery that 3I Atlas appears to be actively transmitting mathematical information through thermal modulation represents a potential paradigm shift in human understanding of extraterrestrial intelligence and communication methods. If confirmed, these prime number messages would constitute the first verified example of interstellar communication, fundamentally changing humanity's cosmic perspective and confirming that we are not alone in the universe through the universal language of mathematics. The Watchers and the Watched. How has the arrival of 3I Atlas fundamentally transformed humanity's understanding of our cosmic significance and role in the galaxy? The implications of this interstellar visitor extend far beyond simple astronomical discovery, forcing a complete inversion of humanity's traditional perspective on extraterrestrial contact and cosmic observation. For centuries, humans have positioned ourselves as the observers, scanning the skies, searching for signs of life, and assuming we were the cosmic detectives investigating an empty universe. The potential artificial nature of 3I Atlas, combined with its apparent mathematical communication attempts, suggests that we have been the subjects of observation rather than the observers. This revelation that advanced civilizations might have been monitoring Earth for thousands of years fundamentally challenges anthropocentric assumptions about human uniqueness and cosmic importance. The object's trajectory through our solar system, timed with humanity's technological advancement and space exploration capabilities, suggests deliberate reconnaissance designed to assess our civilizational development. Professor Avi Loeb theorizes that 3I Atlas represents evidence of a galactic community that has been studying emerging civilizations like humanity, treating us as subjects in a cosmic anthropological study. The mathematical prime number sequences detected in its thermal emissions could represent attempts at first contact using universal mathematical concepts that any technological civilization would recognize. This paradigmatic shift from watchers to watched forces humanity to reconsider our cosmic role, our readiness for interstellar contact, and the profound implications of discovering that we have been under observation by intelligences far more advanced than our own, fundamentally redefining our place in the cosmic hierarchy. As 3I Atlas continues its journey through our solar system, carrying its mathematical messages and thermal secrets, humanity stands at the threshold of the most profound discovery in our history. The James Webb Telescope has shown us that we are not alone, and perhaps never were. For more groundbreaking space revelations that challenge everything we know about the universe, stay tuned to Space Facts. A seismic signal from the moon has just sent shockwaves through the scientific world, and Michio Kaku isn't mincing words. He's calling it a wake-up call for humanity. Kaku warns that this unexpected tremor could mean the moon's core isn't as dormant as we once believed, raising the stakes for both lunar science and life on Earth. Did you know the moon's gravitational pull actually helps stabilize Earth's climate and tides? If the moon is changing, so could our world. Here's a question. Did you know the moon's core might still be active? Seismic signal discovery. A seismic signal on the moon has just thrown the scientific world into a frenzy, and Michio Kaku isn't holding back his concerns. This isn't your average moonquake. This signal was so unexpected and intense that it's forcing scientists to rethink what's happening deep beneath the lunar surface. Kaku, a leading voice in theoretical physics, jumped into the conversation, warning that the moon's core might not be as dormant as we once believed. He explained that for decades, experts assumed the moon was geologically dead, but this seismic activity hints at a mysterious force stirring within. The implications go far beyond curiosity. The moon's core plays a crucial role in stabilizing Earth's tilt and controlling our tides. If something is shifting inside the moon, Kaku warns, it could have ripple effects right here on Earth. Subtle changes in our tides, maybe even our weather. What's even more fascinating is that this seismic event doesn't fit the usual patterns caused by meteor strikes or temperature changes. Thanks to advanced sensors from recent lunar missions, scientists are now picking up signals that were invisible during the Apollo era. Kaku's message is urgent. We're standing at the edge of a new era in lunar science and we need to pay attention. As researchers scramble to decode the moon's signals, one thing is clear: our closest neighbor is keeping secrets, and those secrets might be more important than we ever imagined. Michio Kaku's immediate reaction. When news broke that Michio Kaku had responded to the moon's seismic signal, curiosity skyrocketed across the globe. Kaku's immediate reaction was far from casual. He called the event a wake-up call for scientists everywhere. He emphasized that this wasn't just another blip in lunar data, it could be the first sign of a deeper transformation inside the moon. Kaku's words carried weight, especially as he explained that such seismic activity might point to an awakening of the lunar core, a region long thought to be frozen in time. He urged the scientific community not to underestimate the importance of this signal, warning that ignoring it could mean missing out on a fundamental shift in our understanding of the moon. According to Kaku, the rarity of this event is precisely what makes it so alarming. He drew attention to the fact that our technology has finally reached a point where these subtle signals can be detected and analyzed in real time, making this discovery even more significant. Kaku's passionate call for vigilance resonated with those who understand the interconnectedness of celestial bodies. He made it clear that the moon's fate is tied to Earth's in ways we're only beginning to grasp. As his warning echoes through the halls of science, the world is left to wonder, what else is lurking beneath the surface of our lunar companion, and are we truly prepared for the answers that might emerge? Why the moon's core matters. Beneath the moon's familiar glow, a hidden drama is unfolding that could rewrite everything we thought we knew about our cosmic neighbor. For decades, scientists assumed the moon's core was cold, still, and unchanging, a relic of ancient times. Now, Michio Kaku is sounding the alarm, arguing that the core's activity could be far more dynamic than anyone expected. He highlights how the moon's core, though small compared to Earth's, plays a vital role in shaping the lunar magnetic field and, by extension, the environment that shields the moon from solar radiation. Kaku warns that if the core is indeed waking up, we might see changes in the moon's magnetic properties, which could even affect future lunar missions and technology placed on its surface. The idea that the moon is still evolving deep beneath its crust challenges the long-held belief that it's a geologically dead world. Kaku's insights push us to reconsider the moon's entire history and its ongoing influence on Earth. He suggests that understanding these core processes isn't just an academic exercise, it's essential for predicting how the moon will behave in the future. As seismic signals continue to surface, the scientific community is left with a pressing question. Are we witnessing the rebirth of lunar activity, and what does that mean for humanity's next steps in space exploration? The moon's core, once thought silent, may be trying to tell us a story that's only just beginning to unfold. Potential impacts on Earth. Every so often, a discovery comes along that challenges the very foundation of what we think we know about our place in the universe. Michio Kaku is quick to point out that the moon's core isn't just a scientific curiosity, it's a critical piece of the puzzle that keeps Earth's delicate balance in check. The gravitational pull between the Earth and Moon does more than create tides, it actually helps stabilize our planet's axial tilt, which in turn keeps our seasons predictable and our climate relatively steady. If seismic signals are hinting at changes deep within the Moon, Kaku warns that even subtle shifts could have far-reaching consequences for life on Earth. He explains that a more active lunar core might alter the gravitational relationship between our two worlds, potentially affecting everything from ocean currents to weather patterns. This isn't just a concern for astronomers or geologists, it's a wake-up call for anyone who depends on Earth's natural rhythms, which is, well, all of us. Kaku's message is clear: we can't afford to ignore the moon's signals or assume that its influence ends at the edge of its cratered surface. As scientists race to decode what's really happening beneath the lunar crust, the rest of us are left to wonder how the moon's hidden changes might ripple through our own lives, subtly shaping the world in ways we're only beginning to understand. Historical context. A single seismic signal has upended decades of lunar research, leaving experts scrambling for answers. Michio Kaku draws attention to how past theories about the moon's seismic activity were largely shaped by meteor impacts or the slow cooling of its crust. But this new signal doesn't fit the old script. It arrived with a force and frequency that defies the usual explanations, hinting at processes deep inside the moon that scientists never anticipated. Kaku emphasizes that historically, moonquakes were thought to be rare and easily explained by external events. Now with this unexpected tremor, the scientific community is forced to consider the possibility of an active, evolving core. What's truly captivating is how this event challenges established models of lunar geology. Kaku's warning is that we may have underestimated the complexity of the moon's inner workings all along. The seismic anomaly stands as a stark reminder that even our closest celestial neighbor holds mysteries capable of shaking the foundations of planetary science. As researchers pore over the data, they're left to confront the uncomfortable truth that the moon's story is far from complete. The old assumptions are crumbling, and in their place is a new sense of urgency to understand what's really happening beneath the surface. For anyone fascinated by the unknown, this seismic event is proof that the universe still has plenty of surprises in store. Advanced detection technology. Lunar exploration has entered a new era, thanks to technology that's more sensitive than anything used during the Apollo missions. Michio Kaku highlights how recent advances in seismic detection have pulled back the curtain on the moon's hidden activity, capturing signals that would have gone unnoticed just a decade ago. These new instruments, deployed by international teams and robotic landers, can pick up the faintest tremors from deep within the lunar core. Kaku points out that this leap in technology is a game-changer. For the first time, scientists can monitor the moon's interior in real time, tracking shifts and pulses that reveal its true nature. The seismic signal that sparked Kaku's warning was detected by this new generation of sensors, offering a level of detail that's rewriting the textbooks. It's not just about spotting moonquakes, it's about understanding the moon's ongoing evolution and the forces shaping its future. Kaku stresses that these tools are opening a window into a world that, until now, was shrouded in mystery. The data pouring in is challenging assumptions and pushing scientists to ask bigger, bolder questions about what lies beneath the surface. As the technology continues to improve, Kaku believes we're on the brink of discoveries that could redefine our relationship with the moon, and by extension, our own planet's place in the cosmos. Unanswered questions. A single seismic signal has left scientists with more questions than answers, and Michio Kaku isn't shy about what's at stake. He underscores how little we truly know about the moon's interior despite decades of exploration and countless missions. The recent tremor has exposed a glaring gap in our understanding, forcing experts to reconsider long-held beliefs about lunar geology. Kaku emphasizes that this isn't just an isolated event, it could be the tip of the iceberg, a clue to a pattern of activity that's been hidden for millennia. He challenges the scientific community to confront the unknown head-on, urging deeper investigation and open-minded analysis. Theories are swirling. Could this signal be tied to ancient volcanic processes, or does it hint at something entirely new beneath the crust? Kaku's message is clear. Science thrives on curiosity and the courage to question. He warns against complacency, reminding us that every breakthrough starts with a mystery that refuses to be ignored. As researchers sift through the data, the sense of urgency grows. The moon, once thought to be a silent witness to cosmic history, may be far more dynamic and unpredictable than anyone imagined. Kaku's call to action is resonating across the globe, inspiring a new generation of scientists to dig deeper and listen closer to the stories written in the moon's seismic whispers. Theories and speculation. A seismic mystery on the moon has triggered a wave of speculation among scientists, and Michio Kaku is urging everyone to keep their minds open. Instead of jumping to conclusions, he highlights the need for careful analysis and a willingness to embrace the unknown. Some experts are already floating theories that this signal could be linked to ancient volcanic activity, hinting at a past where the moon was far more alive than we ever imagined. Others suggest it might be the result of the moon's gradual cooling and contraction, processes that could still be shaping its core today. Kaku cautions against settling on easy answers, reminding us that true scientific progress comes from questioning, testing, and sometimes overturning what we think we know. He points out that every seismic anomaly is a chance to uncover new layers of lunar history, clues that could reshape our understanding of how the moon and even the Earth evolved. The excitement is palpable as researchers debate the possibilities, knowing that each new discovery brings us closer to solving the riddle of our celestial neighbor. Kaku's call for patience and rigor is a rallying cry for scientists everywhere. Don't just look for what you expect to find, be ready for the unexpected. In this moment of uncertainty, the moon is offering up secrets that could rewrite the story of our solar system, and Kaku wants to make sure we're paying attention to every detail. Call for international collaboration. Global cooperation is suddenly in the spotlight as Michio Kaku calls for a united scientific front in response to the moon's seismic surprise. He's not content with isolated discoveries or fragmented research. Kaku insists that only by pooling resources, data, and expertise can humanity unlock the true meaning behind these mysterious signals. This isn't just a challenge for one nation or a handful of space agencies, it's an invitation for the world to work together on a cosmic puzzle that could affect us all. Kaku envisions international teams sharing seismic data in real time, cross-analyzing findings, and launching joint missions to deploy even more advanced sensors on the lunar surface. He argues that collaboration is the fastest path to breakthroughs, and that the moon's secrets are too important to be kept behind national borders. The urgency in his voice is unmistakable. If the moon's core is changing, the stakes are global, and so must be our response. Kaku's rallying cry is already inspiring new partnerships and conversations among scientists who might otherwise have worked in silos. As the world tunes in to this unfolding lunar mystery, the message is clear. The universe doesn't care about boundaries, and neither should our search for answers. In this new era of space exploration, Kaku's vision of global teamwork could be the key to understanding the moon and safeguarding our future on Earth. What's next for lunar science? A new chapter in lunar science is unfolding, and Michio Kaku believes the next steps could redefine our relationship with the moon forever. He's pushing for more than just analysis. He wants action. Kaku urges the scientific community to accelerate plans for deploying even more advanced sensors and robotic explorers to the lunar surface, arguing that only with a constant stream of real-time data can we truly monitor the moon's evolving core. He envisions a future where lunar bases double as seismic observatories, feeding information directly to researchers on Earth and enabling instant responses to any new tremors or anomalies. This isn't just about satisfying curiosity. Kaku warns that understanding the moon's inner workings could be critical for the safety of future astronauts, the protection of lunar infrastructure, and even the stability of Earth itself. The recent seismic event is a wake-up call, and Kaku's message is clear. The moon is alive with secrets, and it's up to us to listen. As new missions are planned and international collaborations take shape, the excitement is palpable. Each new sensor, rover, and data stream brings us closer to unraveling the mysteries beneath the moon's surface. For Kaku, this is more than science. It's a race to secure our place in the cosmos, armed with knowledge and united by a shared sense of wonder and responsibility. Thanks for joining me on this deep dive into the mysteries of the moon. If you found these insights as fascinating as I did, don't forget to subscribe to Space Facts for more mind-blowing discoveries from across the universe. Hit that bell icon so you never miss an update, and let me know your thoughts or questions in the comments below. Your curiosity keeps this community thriving, so keep those ideas coming. Until next time, stay curious and keep looking up. Imagine discovering a cosmic time capsule from the ancient galaxy, older than our entire solar system. On July 1, 2025, astronomers spotted something extraordinary racing through space at an incredible 137,000 miles per hour. This wasn't just any ordinary visitor, it was 3I Atlas, the third confirmed interstellar object ever detected, carrying secrets from a part of the galaxy we've never seen before. Discovery of 3I Atlas. What if I told you that finding an interstellar visitor requires watching the entire sky every single night? That's exactly what happened when the Atlas Survey Telescope in Rio Hurtado, Chile, made astronomical history. On July 1, 2025, this powerful sky scanner detected a faint moving object with the temporary designation A11PL3Z. Initially appearing as just a magnitude 18 point of light, the object was traveling through the border regions of constellations Serpens Cauda and Sagittarius. What made astronomers immediately suspicious was its peculiar motion, moving far too fast for any ordinary solar system object. The discovery observations were quickly submitted to the International Astronomical Union's Minor Planet Center, but follow-up observations from both professional and amateur astronomers around the world revealed something extraordinary. This wasn't bound by our sun's gravity at all. Within hours of the initial detection, telescopes across multiple continents were tracking this mysterious visitor, confirming that humanity had discovered another piece of the cosmic puzzle from beyond our solar neighborhood. The object's unusual path through space immediately suggested it originated from outside our solar system, making it only the third confirmed interstellar visitor in human history. Atlas Survey System. Ever wondered how we can monitor threats from space across the entire globe? The Asteroid Terrestrial Impact Last Alert System represents one of humanity's most ambitious skywatching projects. This network consists of 4 50-centimeter telescopes strategically positioned around the world in locations including Hawaii, Chile, and South Africa. Each telescope boasts an impressive 7.4-degree field of view, about 15 times the diameter of the full moon, allowing them to scan vast areas of sky in single exposures. The system operates with military precision. Each telescope surveys 1/4 of the observable sky 4 times per night at approximately 15-minute intervals. With 110 megapixel CCD cameras, these robotic sentinels can detect objects as faint as magnitude 19, while automatically tracking moving objects across multiple observations. The Chilean facility that discovered 3I Atlas represents the cutting edge of this technology, capable of processing thousands of astronomical images nightly, while automatically flagging potential threats or unusual visitors. This automated detection system has revolutionized our ability to spot cosmic wanderers before they disappear back into the darkness of interstellar space. The network's sophisticated algorithms can distinguish between asteroids, comets, and potentially dangerous objects within minutes of detection, providing crucial early warning capabilities for planetary defense. Object classification and naming. Have you ever witnessed the moment when a mysterious space object transforms from unknown to historically significant? The journey from A11PL3Z to 3I Atlas tells a fascinating story of modern astronomical detective work. Initially, when the object was first spotted on July 1, 2025, it received the temporary designation A11PL3Z, following standard protocols for newly discovered moving objects. Within just 24 hours, observations on July 2, 2025 by multiple observatories including the Canada-France-Hawaii Telescope and Lowell Discovery Telescope revealed something crucial: a faint coma and 3 arcsecond tail. This discovery immediately elevated the object's status from potential asteroid to confirmed comet, fundamentally changing how scientists would study and classify it. The Minor Planet Center then bestowed upon it the prestigious designation 3Y Atlas, where 3I signifies it as the third confirmed interstellar object ever discovered by humanity. Simultaneously, it received the official cometary designation C/2025 N1 according to international naming conventions. By the time this announcement was made, astronomers had already collected 122 observations from 31 different observatories worldwide, demonstrating the unprecedented global coordination required to track these elusive cosmic visitors. The rapid classification process highlighted how modern astronomy has evolved to quickly identify and study these rare interstellar objects before they vanish forever. Orbital characteristics. So what does it actually take for an object to completely escape the gravitational grip of our solar system forever? Well, 3I/Atlas possesses orbital characteristics that are honestly nothing short of extraordinary, placing it among the most extreme objects ever studied. Racing through space with a hyperbolic excess velocity of 58 kilometers per second relative to the Sun, this interstellar visitor moves significantly faster than both previous interstellar objects, 1I/Oumuamua at 26 kilometers per second and 2I/Borisov at 32 kilometers per second. Its trajectory follows an extremely hyperbolic orbit, with an orbital eccentricity of 6.141, which is the highest ever recorded for any confirmed interstellar object in human history. This extreme eccentricity makes the comet's path appear almost perfectly straight rather than curved, at least when you look at it from our solar system. 3I/Atlas will reach its closest approach to the Sun on October 29, 2025, passing at a safe distance of 1.36 astronomical units, so that's roughly 203 million kilometers away. Thankfully, Earth remains completely safe during this encounter, as the comet will never approach closer than 1.8 AU to our planet. After its solar encounter, this ancient visitor will continue its relentless journey back into the vast emptiness of interstellar space, carrying with it the gravitational signature of its dramatic passage through our solar system for, well, billions of years to come. Physical properties. So, how do you measure something that's surrounded by a cloud of gas and dust, millions of kilometers away, out there in the depths of space? Determining 3I/Atlas's physical characteristics actually presents some pretty unique challenges, mostly due to its active cometary nature, and all the interference from its surrounding coma. Early estimates suggest the nucleus diameter ranges somewhere between 0.8 to 11 kilometers, though astronomers tend to favor the lower end of this range based on brightness measurements and activity levels. The Gran Telescopio Canarias made a crucial breakthrough between July 2nd and 5th, 2025, determining that the nucleus rotates with a period of 16.79 hours. The brightness variations are only 0.2 magnitudes, which actually suggests a relatively round shape. Color observations using the Palomar 200-inch telescope on July 3, 2025, revealed some fascinating details about its surface composition: a GR color index of 0.43 magnitudes, RI of 0.16 magnitudes, and a spectral slope of about 1.3% per 100 nanometers. The comet's absolute magnitude measures approximately 12, which corresponds to a nuclear radius of roughly 10 kilometers, assuming typical asteroid-like albedo values. These measurements, though, become increasingly difficult as the comet develops a more extensive coma, making it really challenging to distinguish the solid nucleus from all the surrounding ejected material that creates that classic fuzzy appearance. Advanced imaging techniques and computer modeling are being used to separate the nucleus signal from the contaminating coma light. Comet activity features. So what makes 3I/Atlas behave more like 2I/Borisov than the mysterious and inactive 1I/Oumuamua? Unlike the first interstellar visitor, which showed no cometary features whatsoever during its passage, 3I/Atlas actually displays clear signs of vigorous activity even while it's 4.5 astronomical units from the Sun, much farther out than most solar system comets start showing activity. The comet exhibits a distinct fuzzy appearance in telescope images, which indicates a well-developed coma, a cloud of gas and icy dust particles ejected from the nucleus surface as solar radiation heats up volatile materials. Spectroscopic observations by Gemini South and the NASA Infrared Telescope facility on July 5th and 14th, 2025, confirmed that the coma contains water ice and silicate grains with radii of about 10 micrometers. The dust cross-section within 10,000 kilometers of the comet measures 230 square kilometers, assuming an albedo of 0.10. As solar heating intensifies the sublimation process during its approach, micrometer to millimeter scale particles are ejected at speeds ranging from 0.01 to 1 meter per second, resulting in a dust mass loss rate of 0.1 to 1.0 kilograms per second. This activity level suggests the presence of highly volatile ices that have remained frozen for billions of years, potentially preserving ancient chemical signatures from its original star system. Amateur contributions. So, how did citizen scientists around the world help unlock the secrets of this remarkable interstellar visitor? Well, the discovery and characterization of 3I/Atlas marked a historic milestone for amateur astronomy communities worldwide. It really shows how modern technology has, democratized space exploration in ways we couldn't have imagined a few decades ago. Let me tell you about Vamshi Kesareddy, a dedicated citizen astronomer. On July 4th, 2025, he achieved something pretty remarkable by successfully capturing 3I/Atlas using a unistellar telescope and measuring its brightness at 17.8 magnitude. This observation potentially represents the faintest object ever detected by the unistellar network, which just goes to show the incredible capabilities of modern citizen science equipment and automated imaging systems. And there's more. Amateur astronomer Sam Dean made some crucial contributions too, by meticulously identifying additional Atlas prediscovery observations from June 5th to the 25th, 2025. This extended the observational arc and really improved the orbital calculations. Meanwhile, the Las Cumbres Observatory Network, using 0.36-meter telescopes at Haleakala and the 2.0-meter Falks Telescope North, provided essential photometric data. They showed light curve variations of less than 0.2 magnitudes over a 29-hour time span, All these amateur contributions proved absolutely invaluable, as 3I Atlas traveled through star-crowded fields near the galactic center. In fact, professional surveys might have missed it entirely, because the dense stellar background creates confusion in automated detection systems. So it's clear that the passion and dedication of citizen scientists are, honestly, making a real difference in our understanding of the cosmos. Surface composition. So, what can the colors and reflected light from 3I/Atlas actually tell us about its ancient origins in a distant star system? Spectroscopic analysis, reveals some fascinating details about this interstellar wanderer's composition and the environment where it formed billions of years ago. Observations using the Very Large Telescope on July 4th and 5th, 2025, didn't detect clear signs of hydroxides and cyanides gases in the coma, placing upper limits on outgassing rates of about 8.2 times 10 to the 26th molecules per second, and 5.6 times 10 to the 23rd molecules per second, respectively. However, the comet's red spectral characteristics did show up in multiple independent observations, with a spectral slope measuring 18 plus or minus 4% per 1,000 angstroms, making it significantly redder than most solar system comets we've studied. The water ice and silicate mineral composition, detected through infrared spectroscopy, suggests a pretty typical cometary makeup, but the comet's distance from the sun during those early observations meant that many volatile compounds stayed frozen solid. Scientists predict that carbon dioxide and carbon monoxide ices are likely present within 3I/Atlas, though these substances haven't yet been detected as gas emissions. Future observations by the James Webb Space Telescope will provide more detailed compositional analysis as the comet gets closer to the sun and becomes more active, potentially revealing the pristine chemistry preserved from its formation environment. Interstellar object density. So just how common are these cosmic visitors from beyond our solar system wandering through the galaxy? The discovery of 3I/Atlas actually provides crucial insights into the population density of interstellar objects that have been ejected from their parent star systems and now drift through the vast spaces between stars. Based on 3I/Atlas's characteristics and the circumstances of its detection, astronomers calculate a spatial number density of approximately 1 in 1,000 objects per cubic astronomical unit for objects with radii greater than or equal to that of 3I/Atlas. This means that within a cube of space measuring 1 astronomical unit on each side, we might expect to find about 1 object of 3I/Atlas's size or larger every 1,000 such volumes throughout local interstellar space. The rapid succession of interstellar discoveries, first one I/Oumuamua in October 2017, then 2I/Borisov in August 2019, and now 3I/Atlas in July 2025, suggests these objects may be far more common than previously thought by theoretical models. Statistical models now indicate that millions of such objects likely pass through the outer solar system undetected each year, basically invisible to our current detection capabilities. The Atlas network's improved sensitivity and comprehensive sky coverage now mean we're finally reaching the detection threshold necessary to regularly spot these ancient wanderers from distant stellar neighborhoods. Origins and age speculation. Could 3I/Atlas actually be older than our entire solar system, carrying materials from the early galaxy? The comet's extreme velocity and unusual trajectory provide some tantalizing clues about its ancient origins in a very different cosmic environment. Moving at 58 kilometers per second relative to the Sun, 3I/Atlas likely originated from the Milky Way's thick disk, which is a region populated by older stellar populations that formed when the galaxy was younger and chemically different. This suggests the comet could be at least 7 billion years old, which is significantly older than our 4.6 billion-year-old solar system, and potentially containing pristine materials from the early galaxy. The thick disk connection indicates 3I/Atlas formed around low metallicity stars that existed when heavy elements were much rarer throughout the cosmos. Its high velocity suggests it was violently ejected from its parent system through dramatic gravitational interactions, possibly involving massive planetary bodies or close stellar encounters that flung it into interstellar space. The comet's water-rich composition and early activity patterns support theories that it formed in the outer regions of an ancient planetary system, where volatile ices could condense and survive for billions of years in the cold depths of space. This cosmic time capsule really offers an unprecedented opportunity to study materials that predate our solar system's formation. As 3I/Atlas continues its epic journey toward the Sun, reaching closest approach on October 29, 2025, it carries with it secrets from the ancient galaxy that we're only beginning to unlock. This remarkable visitor reminds us that space is filled with wandering worlds, each telling a unique story of cosmic evolution. For more mind-blowing space discoveries that challenge everything we thought we knew about our universe, make sure to like, share, and subscribe to Space Facts, where the cosmos reveals its greatest mysteries. On September 26, 2022, NASA's DART mission slammed into asteroid Dimorphos, shortening its orbit by 32 minutes, a jaw-dropping 26 times the shift scientists predicted. We didn't merely tap a space rock, we rewrote the playbook on planetary defense in a single, spectacular collision. Earth just proved it can shove mountains in the vacuum of space. Will we do it again when everything's on the line? Did you know one well-aimed kinetic strike could steer a city-killer asteroid clear of our planet? The DART mission. Space debris just became humanity's new superpower. What started as NASA's most ambitious planetary defense experiment turned into the discovery that could save our planet from extinction. On September 26, 2022, the DART spacecraft slammed into asteroid Dimorphos at breakneck speed, traveling 370 million kilometers from Earth to execute what many called humanity's first real-life superhero moment. But here's where everything went beautifully wrong. Instead of the predicted tiny 73-second orbital shift, something absolutely mind-blowing happened that left scientists speechless and completely rewrote the rules of planetary defense. The double asteroid redirection test wasn't just about proving we could hit a cosmic rock the size of a football stadium. This was our species taking its first serious swing at playing cosmic billiards, testing whether we could actually nudge a potentially dangerous asteroid off course before it ruins everyone's day. Launched back in November 2021, DART had one job: crash into Dimorphos, the smaller moon orbiting the larger asteroid Didymos, and see what happens when human engineering meets ancient space rock. Scientists expected a gentle nudge, a small proof of concept that might buy us some confidence for future planetary threats. What they got instead was a masterclass in cosmic physics that exceeded their wildest calculations and fundamentally changed how we think about defending Earth from asteroid impacts. Impact results analysis. The cosmic equivalent of hitting a home run when you were just trying to bunt. When the dust literally settled after DART's kamikaze mission, astronomers pointing their telescopes at Dimorphos couldn't believe what they were seeing. The Hubble Space Telescope and ground-based observatories worldwide detected something that made every planetary scientist do a double-take. This wasn't the gentle tap they had modeled in their computers. The asteroid's orbital period had shifted by an astronomical 32 minutes, not the modest 73 seconds they had predicted. That's like expecting to move a boulder an inch and accidentally launching it across the parking lot. But here's where the real detective work began. The impact results analysis revealed that Dimorphos had essentially turned into a temporary comet, spewing out a massive debris plume that acted like a natural rocket engine. This wasn't just impact physics. This was discovering that asteroids could become their own propulsion systems when hit just right. The momentum transfer was 26 times greater than expected, meaning NASA had accidentally stumbled upon a planetary defense cheat code. Scientists frantically recalculated everything they thought they knew about asteroid deflection, realizing that a relatively small spacecraft could potentially redirect city-destroying space rocks with far less effort than anyone had dared hope. The implications were staggering. Humanity's cosmic insurance policy had just gotten a massive upgrade, and all it took was one perfectly executed space crash. Momentum enhancement discovery. Sometimes the most incredible discoveries happen when your experiment works too well. The momentum enhancement discovery from DART's impact wasn't just a pleasant surprise, it was a complete game-changer that sent shockwaves through the planetary defense community. When scientists analyzed why Dimorphos got knocked around like a cosmic pinball instead of just gently nudged, they uncovered physics that Hollywood couldn't have written better. The secret ingredient? That spectacular debris cloud wasn't just pretty space fireworks, it was functioning as an improvised rocket engine, blasting material away from the asteroid and creating additional thrust that multiplied the deflection effect beyond anyone's wildest dreams. This momentum enhancement effect revealed something extraordinary about how kinetic impactors actually work in the real universe versus computer simulations. The ejected debris acted like exhaust from a rocket, pushing Dimorphos in the opposite direction with tremendous additional force. It's like throwing a baseball and having it somehow gain speed mid-flight. Completely counterintuitive but absolutely real. The 26-fold multiplication of expected results meant that future planetary defense missions could potentially redirect dangerous asteroids using much smaller spacecraft than previously thought necessary. Scientists realized they had witnessed something that could revolutionize how humanity approaches asteroid threats. Instead of needing massive, expensive missions to deflect city-killer asteroids, relatively modest spacecraft could potentially do the job thanks to this newly discovered physics phenomenon. The universe had just handed humanity a cosmic cheat code for planetary defense, wrapped up in the most successful space crash in history. Asteroid structure insights. Some asteroids are basically cosmic sandcastles waiting to fall apart. The asteroid structure insights from DART's encounter with Dimorphos completely shattered our assumptions about what these space rocks are actually made of. When mission scientists dove deep into analyzing why the impact was so devastatingly effective, they discovered that Dimorphos wasn't the solid, monolithic boulder they had expected. It was what researchers now call a rubble pile, essentially a loose collection of rocks, dust, and debris held together by nothing more than weak gravitational forces. This revelation explained everything about the spectacular 32-minute orbital change and why the debris plume was so massive. Think of it like the difference between hitting a concrete wall versus a pile of gravel. The energy transfer is completely different. When DART slammed into this cosmic rubble pile, it didn't just create a neat crater like punching solid rock. Instead, it excavated enormous amounts of material, launching chunks of Dimorphos into space and creating that dramatic comet-like tail that telescopes tracked for weeks. This discovery fundamentally changed how scientists classify near-Earth asteroids and assess potential planetary threats. The loose structure meant that kinetic impacts could be incredibly effective against similar rubble pile asteroids, potentially making planetary defense missions far more successful than anyone had dared hope. But it also raised new questions. How many potentially dangerous asteroids share this loose, fragmented structure? The answer could determine whether future deflection missions are routine procedures or complex engineering challenges requiring completely different approaches. Strategic implications. One successful space crash just upgraded humanity's survival odds by millions. The strategic implications of DART's overwhelming success rippled through every space agency and planetary defense program on Earth, fundamentally reshaping how we approach the cosmic threat of asteroid impacts. When the momentum enhancement discovery proved that deflecting dangerous asteroids could be 26 times easier than previously calculated, it wasn't just a scientific breakthrough. It was a species-level game-changer that moved us from theoretical planetary defense to proven, practical capability. Military strategists, space engineers, and government officials suddenly realized that protecting Earth from city-killer asteroids might not require the massive, expensive missions they had been planning for decades. The implications extend far beyond just building bigger rockets or spending more money. This discovery means that relatively small, affordable spacecraft could potentially redirect near-Earth objects that pose existential threats to human civilization. Space agencies worldwide began recalculating their planetary defense budgets, realizing they could potentially defend against multiple asteroid threats with the same resources previously allocated for single missions. The kinetic impactor technique went from experimental concept to proven technology overnight, giving humanity its first real planetary defense weapon that actually works better than designed. But perhaps most importantly, the success demonstrated that we don't need decades of warning to mount an effective defense. The momentum enhancement effect means faster, more responsive missions could potentially handle threats detected with shorter lead times, dramatically improving our cosmic security posture. Hera mission planning. The real investigation starts now. While DART proved that humanity can successfully punch asteroids off course, the European Space Agency wasn't about to let this cosmic crime scene go unexamined. Enter Hera mission planning, the detective work that will finally reveal exactly what happened when our spacecraft obliterated Dimorphos, and why the results were so spectacularly beyond expectations. Scheduled to launch in 2024, this follow-up mission will arrive at the Didymos system in 2026 to conduct the most detailed forensic analysis of an asteroid impact in human history. Think of Hera as the cosmic CSI team, arriving to photograph the crater, measure the debris, and piece together every detail of humanity's first successful planetary defense demonstration. But Hera isn't just satisfying scientific curiosity, it's gathering critical intelligence for future planetary defense missions. The spacecraft will precisely measure Dimorphos's mass, analyze the crater's dimensions, study the asteroid's internal structure, and determine exactly how much material was ejected during impact. This data is absolutely crucial because the next time we need to deflect an asteroid, it won't be a test. It could be the difference between civilization and catastrophe. Hera's findings will help scientists understand whether the momentum enhancement effect was a lucky accident or a predictable phenomenon that can be reliably reproduced. Armed with this knowledge, future deflection missions can be planned with surgical precision, ensuring that when humanity faces a real cosmic threat, we'll know exactly how hard to hit it. Planetary defense evolution. From asteroid hunters to cosmic guardians in just one successful crash. The planetary defense evolution triggered by DART's triumph represents the most significant shift in humanity's approach to cosmic threats since we first started tracking near-Earth objects. Before September 2022, planetary defense was largely theoretical. Scientists could model asteroid impacts, calculate trajectories, and propose deflection strategies, but nobody actually knew if any of it would work when push came to shove. Now, with real data proving that kinetic impactors are devastatingly effective, space agencies worldwide are completely rewriting their threat assessment protocols and emergency response procedures. The momentum enhancement factor isn't just being incorporated into computer models, it's fundamentally changing how we categorize asteroid risks and allocate planetary defense resources. This evolution goes beyond just updating equations and mission plans. Countries that never had serious planetary defense programs are suddenly investing in asteroid detection networks and deflection capabilities. The International Space Station partners are collaborating on advanced warning systems, while private companies are developing rapid response spacecraft that could be deployed within months rather than years. The success has also accelerated development of next-generation asteroid hunting telescopes and improved orbital prediction algorithms. Most importantly, the psychological shift is enormous. Humanity has moved from passive observers of cosmic threats to active defenders of our planet. We're no longer just hoping that dangerous asteroids will miss us, we now have proven technology to make sure they do. The age of planetary defense isn't coming someday. It arrived the moment Dimorphos got knocked sideways by human ingenuity. Mission success redefinition. Success isn't always about hitting your target, sometimes it's about completely redefining what success means. Mission success redefinition became the most unexpected outcome of the entire DART program, fundamentally changing how space agencies measure achievement in planetary defense missions. Before impact, NASA had already declared the mission a triumph simply for demonstrating that humans could accurately navigate a spacecraft across 370 million kilometers and hit a target the size of a football stadium. The primary objective was purely technological: prove the guidance systems work, test the kinetic impactor concept, and measure any detectable change in Dimorphos's orbit, no matter how small. Mission planners would have celebrated even a 10-second orbital shift as groundbreaking proof of concept. But the universe had other plans. When the 32-minute orbital period change was confirmed, it didn't just exceed expectations, it obliterated every benchmark scientists had established for what constituted mission success. This wasn't incremental progress, it was a quantum leap that forced mission planners to completely recalibrate their success metrics for future planetary defense operations. The 26-fold enhancement over predicted results meant that DART had essentially accomplished what multiple missions were designed to achieve. Space agencies worldwide began questioning whether their own success criteria were too conservative, whether they were underestimating human technological capabilities, and how to properly set goals for missions venturing into uncharted scientific territory. The redefinition cascaded through every future mission proposal, with engineers now expected to plan for spectacular success rather than modest achievement. Debris management and safety concerns. What happens when your successful space mission accidentally creates a cosmic mess? The debris management and safety concerns following DART's spectacular impact revealed that planetary defense isn't just about hitting asteroids, it's about dealing with the aftermath of turning space rocks into temporary comets. When Dimorphos got walloped on September 26, 2022, it didn't just change its orbit, it transformed into a debris-spewing machine that kept astronomers busy for months tracking every chunk of ejected material. Ground-based observatories worldwide suddenly found themselves monitoring a massive cloud of asteroid fragments spreading through space, creating an unprecedented challenge in space situational awareness and collision risk assessment. The spectacular debris plume that made DART so successful also raised serious questions about future deflection missions near critical space infrastructure. The ejected material created a comet-like tail visible through telescopes for weeks, with chunks of Dimorphos scattered across thousands of kilometers of space. Mission controllers had to carefully track this debris field to ensure it posed no threat to other spacecraft operating in the region, while also studying its behavior to improve debris modeling for future planetary defense operations. This unexpected consequence highlighted a crucial gap in mission planning. While everyone focused on successfully deflecting the asteroid, nobody had fully anticipated the complexity of managing the resulting space debris. The lesson was clear. Future deflection missions targeting asteroids closer to Earth or near valuable satellites will need sophisticated debris mitigation strategies to prevent turning one cosmic threat into dozens of smaller ones. Precision requirements for real threats. Practice makes perfect, but real asteroids don't give you second chances. The precision requirements for real threats expose the sobering reality behind DART's celebration-worthy success. While humanity proved we can deflect asteroids, the margin for error when facing actual Earth-threatening objects is absolutely zero. Unlike the controlled experiment with Dimorphos, where scientists had years to plan and could afford to overshoot their deflection goals, a genuine planetary defense scenario demands surgical precision that accounts for every variable imaginable. The momentum enhancement effect that made DART so spectacularly successful also introduced a new layer of complexity. Future deflection missions must accurately predict how much debris each target asteroid will eject, because the difference between nudging a space rock safely away and accidentally hurling it toward a populated area could determine the fate of millions. The challenge intensifies when considering that every potentially hazardous asteroid has unique characteristics that could dramatically affect deflection outcomes. Rubble pile asteroids like Dimorphos might respond completely differently than solid metallic objects, icy comets, or loosely bound dust clouds. Mission planners now face the daunting task of developing deflection strategies that work across this entire spectrum of cosmic threats, all while operating under the pressure that failure means catastrophic impact. The years of advance warning required for successful deflection means that asteroid detection networks must identify threats earlier and with greater accuracy than ever before. One miscalculation in trajectory, timing, or target composition could turn humanity's greatest technological achievement into its most devastating mistake. That's how NASA turned one perfectly executed space crash into humanity's greatest planetary defense breakthrough. The DART mission didn't just prove we can protect Earth from asteroid threats, it showed us we're way better at cosmic billiards than anyone dared hope. But this is just the beginning of our journey into the incredible world of space exploration and planetary defense. If you love discovering how we literally punched an asteroid off course, smash that subscribe button and hit the bell icon so you never miss the latest mind-blowing space facts. Drop a comment below. What space mission do you want Space Facts to cover next? The universe is full of incredible stories, and we're just getting started.